Hello everyone, Mr.Waz here, and welcome to WasleyScience. Today we are going to be talking about heat transfer, and I am super excited because we are finally embarking on totally fresh material for you. We are going to start today by talking about the first and second law of thermodynamics. We are also going to be talking about the difference between heat and temperature. And then finally, we're going to talk about three types of heat transfer: conduction, convection, and radiation. Alright, so I'm going to start off with some crazy word here. It's thermodynamics, but it's really not a crazy word. Thermo just means heat. Dynamics means the balance in systems. So it's the balance of heat. That's what thermodynamics means. It deals with how energy flows and moves through our Earth, specifically with heat, and how heat converts to other forms of energy. So this really coincides with what we were beginning to talk about with our last video on energy. I told you this diagram was going to come back. Now, the first law of thermodynamics is that energy can never be created or destroyed. It can change from one form to another. So in this example, what's the source of energy? I hope you immediately realized it was the sun. Now, the one thing about this diagram that's interesting is that it looks like that the energy is gone after it's in your house. And that's simply not the case. With whatever appliance or anything that you're using in your house, there is energy that will leave whatever device it is, usually as heat, and then go into the atmosphere. But it's just such a small impact that it's not very noticeable or really useful to us. So it is important to realize that although this isn't really a circle because that heat doesn't really make its way back to the sun, the energy is always flowing from one form to another, never lost. And again, the amount of energy that we have in this universe has been the same for the past 11.7 billion years when the Big Bang occurred. The first law of thermodynamics is pretty easy to swallow, but the second one is tougher. This law states that when energy changes, it goes from a more useful, more concentrated form to a less useful, less concentrated form. This means that every time we convert energy, we do lose some of it, usually in the form of heat. Now, like I said, when I mean losing energy, I don't mean the energy is lost. I mean it turns into heat that goes into the atmosphere. And the reason for that is that heat can only be transferred from a hotter object to a colder object. Heat likes to move to the colder source. So when it goes into the atmosphere, it's going to go somewhere colder and not very useful to yourself. Now you may be wondering, well, how does an air conditioner work if heat always moves from hot to cold, not cold to hot? Well, you could go ahead and click on this link on the bottom here and see a quick video on how air conditioners work. Basically, there's a chemical reaction inside in which they use a chemical to cause evaporation, and then when this chemical evaporates, it creates cool air, and then a fan blows that cool air into your house, and then they compress that evaporated air back into a liquid and then repeat the process. So it's quite interesting. But again, this is a really big deal that heat only moves from hot to cold. Heat is always trying to equalize an area and reach some sort of equilibrium. The universe is trying to reach some sort of equilibrium for temperature. So heat is always moving to the colder source to try to even everything out. That's what the second law of thermodynamics is really all about. Whoa, I did not mean to rhyme. Alright then. Well, if you want to see somebody do a better job at making a song of thermodynamics than me, then go ahead and click on this link here. It's a classic. I think you will enjoy it. So now let's move on to heat versus temperature. First, heat. Heat is a form of kinetic energy. It can be described as the molecules in motion. Every atom in the universe is moving around. So that means every atom has some sort of heat to it. The faster the molecule is moving, the more heat that molecule has. So even a molecule at 0 degrees Celsius is still moving around. It's vibrating in place, if it's water, for instance, but it's still moving and has heat. Heat is the total amount of kinetic energy. Now, I know that's not going to make a whole lot of sense to you right now at this moment, but do yourself a favor, underline that word total and put a couple arrows around it. It'll make a lot more sense when we talk about temperature. Heat is measured in calories. As far as calories go, it takes 1 calorie to raise the temperature of 1 milliliter of water 1 degree Celsius. So that's why they use it. Now, just to give you some perspective, if you have like a Nalgene bottle of water, there's about 1,000 milliliters in that, 1 liter. So it would take 1,000 calories to raise your Nalgene bottle 1 degree Celsius. Now, here's a little bit more on calories. 1,000 heat calories is equal to 1 food calorie. So if you eat a Snickers, which has like 300 calories, food calories, you actually had 300,000 heat calories. But if you ran a 5K, which is 3.1 miles, you may burn 600 calories, and you actually burn 600,000 calories. So you can go have 2 Snickers. And then 1 heat calorie is actually equal to 4.184 joules. So if you want to see more things on calories, you can go ahead and click on the link up here. There's a YouTube video for you on what exactly 200 food calories looks like. And then down here, this diagram is actually really useful because it shows you how many calories it takes to melt ice and to evaporate water. So it takes around 80 calories to melt ice to turn into a liquid, but then you can see here that it takes 600 calories to evaporate water into a gas. And the reason I wanted to show you this is because we're going to talk about this later, but it takes a lot more heat to evaporate water than to melt ice. So that's just the one thing I wanted to show you with that diagram there. So now that we've talked about heat, let's talk about temperature. Temperature is the average speed of the atoms and molecules, and I want you to underline average speed. That's the really important part, and that's what makes it different than heat. So let's get into this further. Let's say we have 10 molecules of water at 0 degrees and 10 molecules of water at 100 degrees. Not saying we necessarily mix them all together, but what would be the average temperature of those 20 molecules? And just think 0, 100, there's an even amount of them, so that average would be 50 degrees. So the average, so if you put a thermometer in between those molecules, the thermometer would read 50 degrees. It wouldn't just suddenly read 100 and then 0. It would read 50 degrees. That's what thermometers do. They pick up the average speed of the molecules around them. There's molecules around every thermometer that are hotter than what they are reading and also colder. They're just picking up the average. Kind of think of it like this diagram on the bottom here. Look where Connecticut is. Connecticut is yellow, so that would mean that its annual mean temperature is 50 degrees. Well, I can tell you right now the temperature outside is not 50 degrees, and it's not really 50 degrees a whole lot in the year. But overall, throughout the entire year, if they took the temperature at every single given moment throughout every single day, the average comes out to 50 degrees. That's kind of what a thermometer is doing, but all the time with the air around it. So this table is really important. It shows the 3 main scales for measuring temperature: Fahrenheit, Celsius, and Kelvin. You're probably not really familiar with Kelvin, so we will get to that. But Celsius is what we use in science. We will always be using Celsius throughout the year because it just makes a lot more sense. And also, the rest of the world uses it. United States of America is one of the few countries that uses Fahrenheit, and we really need to just get with the program here. But at 0 degrees Celsius, that's when water freezes. That's really easy to remember. We have to remember 32 degrees Fahrenheit. It's just a really annoying number. And just to add to that, water boils at 212 degrees Fahrenheit. That's also really annoying to remember. Where with Celsius, 100 degrees. Really easy. Celsius was designed specifically for water because water freezes at 0. They set it so that water would freeze at 0 and boil at 100. With Kelvin, Kelvin is just, you just take your degrees in Celsius and you add 273, and that will be your degrees in Kelvin. Now, the thing about Kelvin, what makes it important, is the coldest you can possibly get, and this doesn't even really exist around in the universe, is a number called absolute zero, which is 0 Kelvin. And at absolute zero, the atoms are not even vibrating. So they're not only are they not moving around, but they have stopped vibrating. So this is a temperature that scientists have been trying really hard to get. So yeah, we won't be using Kelvin throughout the year, but we will be using Celsius. Alright, this is a really useful slide here. This is when we finally get to compare heat versus temperature. So again, heat is the total amount of available kinetic energy you have, and temperature is the average speed of the molecules. So a burn-in match, it has heat, and it also has temperature. The temperature of this burn-in match is 451 degrees Fahrenheit or 232 degrees Celsius. 100 burn-in matches will still have the same temperature because remember, temperature is the average speed of the molecules. So it still has a temperature of 451 degrees Fahrenheit. But 100 burn-in matches has 100 times more heat than one burn-in match because heat is the total kinetic energy. There's a great example we'll be talking about in class in which you have like a really hot cup of water that's like boiling, so 100 degrees Celsius, and then you have a bathtub which is around 50 degrees Celsius. Which one has more heat? And you just think, well, which one has more water? Because the one with more water would have overall more moving molecules in it than just a little cup of water. Sure that the cup of water has faster molecules moving, but the bathtub has so many more molecules, so that would have much more heat. And I have an oldie but goodie here. If you click on the top left here, this is a Eureka video. It's really old, but it explains heat and temperature very well. It impresses me. So if you'd like to click on that for a good review. And I know I've already given you guys a song, but if you want to torture yourself, go ahead and click on that. It's bad. But if you're feeling in the mood, go for it. Alright guys, we're getting there. We're on our last part here, which are the 3 transfers of heat. The first one we're going to talk about is conduction. Conduction is when heat is passed from one molecule to another through collision. Touching is required. So if there is no touch, then there is no transfer of conduction. So one thing about this, it seems really easy. You touch fire, then you're going to transfer heat through conduction. You put your hand on that burner on the stove, you're going to transfer heat to your hand by conduction. But One thing I do need to emphasize with conduction is whenever there is contact with anything, you're transferring heat through conduction. You are, whenever, because there's crashing molecules. So if I clap right now, my hands are starting to get hot because I am causing molecules to crash into each other. This person here kicking the soccer ball, they are transferring heat by conduction to the soccer ball, which is causing the soccer ball, and the force itself is causing the soccer ball to launch. But there is heat on that soccer ball from that foot. So that's something that's really important with conduction. All right, let's move on to the second one here, which is convection. Convection will seem a little tricky at first, but it's going to make sense. So convection is when heat is passed when the hot fluids, like liquids and gases, convection does not occur with solids. Very important. But when the hot fluids rise and then the cool fluids sink. And this is caused by density differences. There it is. There's density. Told you it was coming, guys. So, since heat is molecules in motion, the hotter something is, the faster the molecules move. So they'll want to spread out and get away from the source that is heating them. So they can heat the area that is less warm. And then that will push the things that are less warm closer to the source of heat. And what ends up happening is a sort of circular motion here in which the warm air will rise and push down the cool air, and then the cool air will get to the source and then become heated and then go back up. And that's what happens with any radiator, and that's what happens when you boil water. So this is the source of heat. So the molecules are being heated on the bottom and they're going up, and they push down the molecules that have been away from the heat source for the longest period of time. And then they become heated, and by the time they become heated and move back up, those molecules that were once on the top are now no longer hot. So then they get pushed down. And convection is caused by density differences. Alright guys, we're on our last one here, so let's finish this off. Last one is radiation. And that is when heat spreads out in every direction. It radiates out as electromagnetic waves. And I don't just think about it like on a plane. Think about it like on a total 3D spherical sort of way. It radiates in every single direction, up, down, diagonal, you name it. And it radiates out as electromagnetic waves. Radiation is the only way that energy can be transferred through empty space. Radiation is a big deal. So the reason why the sun is able to give us energy is because of radiation. So this is just a diagram here that shows some radiation. I'd like you to kind of look at this diagram and see if you can locate the source of heat. I hope that you picked at x at 0, because you can see that the heat is being radiated out. Alright, so here's like my favorite diagram for the transfer of heat. This diagram is awesome because it has all three transfers of heat on one. And it's the classic boil in a pot of water diagram. So this stupid guy grabbed the handle, and he is having some heat transferred to right to his fingertips because the handle is made of metal. And I don't know why they designed it that way. But yep, he's getting burned through conduction. If he didn't touch it, then he wouldn't feel any heat from conduction. But he would feel heat from radiation because the source, the fire here, is radiating heat out, and you would feel that heat. Now inside of the pot, the water is being boiled, and like we talked about before, the molecules that are right at the source here are going up and then pushing down the molecules, forcing them down back to the source so they can be heated, because that convection has everything to do with the second law of thermodynamics, which is heat moves from hot to cold. I would definitely draw this diagram out. So why is this all important with earth science? It's really important because our weather is caused by all three: radiation, conduction, and convection as air moves up and then moves away from the source, moves away from the surface being heated, and then comes back down. Earthquakes, volcanoes, and tsunamis, they're all caused by convectional currents that are inside the Earth, which we're going to talk about quarter 2. Credits to some of the material on this presentation goes to John Schwartz and Karen Contorno. Hi guys, so we've reached the end at this point. Please remember to subscribe. If you click on the bottom here, you can subscribe to WasleyScience, my channel. So I've given you enough videos at this point, so I thought what would be good for you is to kind of quiz yourself. So go ahead and try to fill in the blanks to prepare yourself for tomorrow, because you never know what could happen. Alright guys, take care.